just a couple announcements before we get started. We have a midterm on March 19th. We'll be doing this in the review session room at that room. So you'll get 2 hours out of that. So I usually do something, if you've taken one of my classes before, we are going to do the yes, no, maybe thing. And so I got hired quite a few years ago, people asking me, is it on the exam? Is that going to be on the exam? What's on the exam? And I kind of get it. So to soothe your anxiety, I'll answer the question. We'll write on the board 3 columns, and you can ask me things. And so what I'll probably do for the yeses, if you get it right, what I usually do is I make an exam with maybe 8 questions. And then I have 4 or 5 of them selected from that I'll give to you. So if you can name those questions, I'll put them into the yes column. I'll try to make that column very small. So, but this is an opportunity for you. So we'll do that on Wednesday evening, and I'll get a room for us. We'll be coming back to ancillarity. We're in the middle of a conversation about ancillary statistics, and the definition itself is a little bit misleading in the sense that ancillary statistics marginally on their own don't have any information about the parameters you're trying to infer. However, that does not necessarily mean that they're orthogonal to minimal sufficient statistics. There can be some overlap in the information. And so saying that, they're not all that useful in principle. So there is something called the conditional frequentist, the conditions on the right ancillary statistic, but it's a bit of a broken paradigm because you don't have a general methodology for coming up with the right ancillary statistic to condition on. We'll come back to that conversation and run through a couple examples. I think this is a self-contained lecture, the likelihood principle, and so we're going to pick up with this. And this is something that's hotly debated. Probably if you're in your 50s, a statistician, you probably went through a period where you just fought over this thing. Either you argued for it or you argued against it. And that's happened on this campus as well. So a couple of years ago, this was actually last spring, Jim Berger came in. So Jim Berger's a powerful statistician, wrote a decision theory book and basically said something about Bayes' optimality. And in his books, he argues the likelihood principle. He wrote a book on the likelihood principle. And there's a department here on campus, the philosophy department, and they have a statistical philosophy group. And they like to argue against the likelihood principle. So when Jim was here, they came up as an entourage, and it seemed like the 60s. So a little hot debate. So back and forth. So it never gets old, I guess. So there's supposed to be a proof of this statement, the likelihood principle, but I'll warn you that it's unclear if there is a proof that exists. And so some people say there's valid proofs, and then other people come back and say not valid. So in Jim Berger's book, chapter 4 of the likelihood principle, he supplies a proof of the statement I'm about to make. And in my version of this book, there's an asterisk on chapter 4 that says this can be omitted because there is a mistake in there. And so Deborah Mayo here that was running the stat philosophy group, she says she has a proof on why the likelihood principle is not right. She published on that a few years ago, and that proof has been debunked as well. So every proof that I know of about the likelihood principle, whether it's true or not, has been debunked one way or the other. So I do think this is a useful principle, so I'm going to just say that. I don't know if this is truth, gospel, how you want to take it, but I think it's useful. And so it's a statement about conditioning on data and using sufficient statistics. So it seems like a good thing to do. Likelihood functions are conditioned on the data. It's a conditional statement about the data. Sufficient statistics all have the information about the parameters themselves. And so the proof concerns whether or not the sufficiency principle, which we've studied, and the conditionality principle, i.e. you're supposed to condition on your data, make you, let me say this right, force you to believe that the likelihood principle is a fact. And I don't think that's true. Saying that, the likelihood principle makes you abide by the sufficiency principle and the conditionality principle, because likelihoods have both properties. So the proof is a statement about whether or not the likelihood principle you have to follow because of that. You don't have to do anything. There's all kinds of interesting things out there that violate the likelihood principle, and I do it regularly. The biggest problem with the likelihood principle, I'll write it down in just a moment, is that you never have model in hand. And so again, it's kind of a fiction. So, but I'll show you an example where maybe I can exemplify that if you break the likelihood principle or if you violate it, there can be repercussions to that. And so I think the best argument in favor of the likelihood principle is not the debunked proofs, but rather the examples. So we'll focus on that. Birnbaum in the 60s came up with the first proof. It kind of shocked the world. The Bayesians ran in and said, this is a statement suggesting you have to be a Bayesian. And that's the part that really upset everyone. And why the field started to tangle with each other. So here's the statement. And I'll phrase it the way the book does. We're going to confront our two experimenters again. So same two experimenters from last time. In our last example, our two experimenters that we compared didn't agree with each other. In this example, they're going to have more agreement. And so experimenter 1 gets to see data set X, just some general data set. And experimenter 2 sees another data set. And they're both interested in inferring the same parameter, theta. Okay, so theta is just a concept, some parameter you don't know. So the statement is this. If the likelihood function for experimenter 1 is equal to some constant, which is just a function of x and y, not the parameter itself, times the likelihood for experimenter 2, then experimenter 1 and 2 should make the same inferences about theta. Okay, so experimenter 1 and 2 compute their likelihood and figure out that this equality holds. Likelihood principle says they should make the same inferences. It's not that contentious of a claim. I kind of like it. I kind of believe it. I think so too. But I don't know if there's a proof. What does this say? What does this even mean? What's the statement? How would I address that in words? Why is this true? I think I stared at it in graduate school and I was like, what the heck? Now I look at it and I say, obvious. I kind of agree. But what does that mean? It's just an equation. Let me write this differently. It says this. Likelihood of theta x is proportional to the likelihood function for experimenter 2. So it's just a statement. There's no theta in there. So it's saying that these two likelihood functions are proportional to each other. So they have the same shape. That's it. So this is just the same shape. Likelihoods have the same shape. Draw your picture. Experimenter 1 is doing their experiment, and they compute this likelihood function. Like this. These are my likelihood functions. And this is a function of theta. Experiment 2 likelihood function looks like this. If I could draw, I'm trying to draw the same height, the same shape, but changing the height. So this is just a fixed distance right here. That is likelihood under 1. So that's all it's saying. So we've said this all along. When we looked at the sufficiency principle, we said the sufficiency principle is really this thing, where I take the ratio of a sampling distribution of all the data compared to the sampling distribution of the statistic. If that ratio is constant, that statistic is sufficient. And I've been saying what we're really doing is dividing the likelihoods, and comparing to each other and showing that that thing's a constant. So this automatically implies the sufficiency principle right here. And they're both conditioning mechanisms. So they're tools for conditioning on the data. So it also adheres to the conditionality principle of the book. So the contentious statement is experimenter 1 and 2 will make the same inferences about theta. Do they have to because of this? And I don't think you have to do anything. But I will show you a violation of the likelihood principle that leads to maybe some poor inferences. Any questions about this before we look at an example? So again, I think that the best argument in favor of the likelihood principle are the examples. I heard somebody say that to me when I was maybe in my 3rd year of graduate school, and it's like, what are you talking about? There's a proof. And now I get it. And so I was just part of this contagious argument. The proof's arguable. We won't go into those details, just because we'll debate forever about it. Okay, here's an example. Let's say you observe data. Some set of data. Let's say it looks like this. Let me give you my mechanism for the data. I'll say probability of a head is P, and probability of a tail is 1 minus P. So Bernoulli sampling. This is just a Bernoulli distribution. I'm going to flip a coin. And then I'm going to call those sides instead of 1s or 0s, we'll put heads or tails. And so this is what experimenter 1 gets to observe. Experimenter 1. Now, I want you to forget the way that I just wrote that down and the order of everything, so you didn't observe that. So experimenter 1 just walks up and says, hey, here's the data. Experimenter 2 observes this data. Don't watch me. Don't get to actually see this happen. So experimenter 2, they're in their laboratory and they see that. Experimenter 1's over in his laboratory and he sees this. They're the same, right? They look identical. So there's a little bit of a disagreement between the two. They both agree on this. Both experimenters get to know this mechanism for generating the data. So just coin flipping. And it's not that contentious to think that if both scientists, experimenters, saw this data, that they should make the same inferences about P. So the goal here is to try to learn what P is. But experimenter 1 and 2 think different things about how this data was generated. They agree on the fundamental mechanism, but experimenter 1 thinks the data was created with a pre-fixed stopping rule where n was fixed. So experimenter 1 believes the coin was predetermined to be flipped 10 times. They don't know why you stopped flipping the coin, essentially. So experimenter 1 makes an assumption that the data was collected in such a way that there was a predetermination that the coin would be flipped 10 times. That's what they saw. Experimenter 2 believes that you were going to flip the coin until you observe the 5th head right here. Just make that C. So basically they see the same thing, they agree on the model, but they disagree on why the coin stopped flipping. And this is like a situation that we find ourselves all the time. Why was the data this long? So why did this many things come in? We might understand the fundamental mechanisms. So this is a pretty simple model right here. In experimenter 1 and 2, you might already realize have the same likelihood functions. So they should make the same inferences. We'll write them down in just a second. So let's put a little bit of math to this. 2 questions. How is X and Y distributed? They're not trick questions. Let's start with this one. What's the distribution of this random vector of data? What's that?
Binomial.
It's binomial. So because we think n was fixed. So x with n fixed, it's binomial. Y with the number of heads, the 5th head occurring on the last event, that has a different distribution. Does anybody know what it's called? Negative binomial. Sums of geometrics. So y is negative binomial. Good job. Now there's a couple different ways you can parameterize the negative binomial, and I'll go through it in more detail when we come back from spring break. But let me show you how I always derive the negative binomial, because I can't ever remember what the normalizing constant is. And so, let me show you what it is. me just ask you, did the experimenters see the same data? Yeah, so maybe. I say no, because the stopping rule is part of this stochasticity. And so I would say they didn't see exactly the same thing. It looks the same on the chalkboard, but the mechanism for stopping is part of this equation. So I'd say they almost do. They disagree on one subtle thing. So let's just me show you what a negative binomial looks like. First, let's just do this. So probability x is equal to 5 right here. So this is just a binomial random variable. So this is for experimenter 1. They see this thing. I'll just say probability of x is n. Choose x, whatever the number is, how many successes they saw. So x is that random variable. N choose x, p to the x, 1 minus p, n minus x. So that's experimenter 1's sampling distribution. And we all know that. We see this all the time. Experimenter 2's looks a little bit different. I'm going to derive the negative binomial distribution for you, and so you'll never get confused about this after you see this picture. So what's the probability that this thing happened right here? It's just p. This happens with probability p. And this thing in experimenter 2's distribution has to be fixed to be the last entry. Can't move that anywhere. So if experimenter 2 thinks that the stopping rule is the 5th head, this was predetermined at the end to be a head. Let me just ask a quick question. If somebody was having this debate with you, whether or not that vector of data was binomial or negative binomial, how could you solve the debate? In practice, say you saw two people just fiercely arguing about this. It's not going to happen with words. You don't know. So what I would do is go get another vector of data. And if I kept seeing that the vector of data was of size 10 over and over and over again, and I saw that the last entry was fluttering, I would know which distribution it came from. So this is a little bit contentious. Experimenter 1 and 2 don't have the opportunity to go do that. They're just stuck with this. It's just an argument. This stuff right here can have any ordering to the heads or tails, just as long as there's 4 heads over here and 5 tails. So this is the probability distribution for this part of the data. It's just the probability of observing four heads and 5 tails. Order doesn't matter. It's just exchangeable data. We're just flipping the coin. So the order there didn't matter. All we have the ordering on is the very last entry. And so I can work out this probability. So this is binomially distributed right in here. So this is just out of 9 things, I'm going to choose some number of tails. So this right here has probability 9, choose 4. P to the 4. 1 minus P to the 5. So this part is binomially distributed. Just write that down. So I always derive it this way. And I multiply these two things together. This times this is equal to 9 choose 4. P to the 4 times P, P5, 1 minus P to the 10 minus 5. We'll just put 5. So experimenter 2's likelihood function is that. For experimenter 1, we can actually plug in the numbers as well. So experimenter 1 gets to actually see 10 choose 5, p to the 5, 1 minus p, 10 minus 5, which is just 5. I'll write it down that way. So this is experimenter 1's likelihood function. I just used the sampling distribution and plugged in what I think was a random thing, which is the number of successes. So experimenter 1's random variable is the number of successes. Experimenter 2's random variable is different. So what is experimenter 2's random variable? It's not the number of successes. That was predetermined to be fixed at 5. What's that?
Number of flips.
The number of flips, or the number of failures. You can parameterize that 2 different ways. So when you look at your book, be careful which way they're parameterizing it, which part is random. So either the number of flips is random, or the number of failures is random. Those are equivalent statements, because the number of successes is fixed. So there's a different random variable here, but this part of the equation agrees. And so these 2 things are proportional to each other. And they should make the same inferences because of that. And I'll tell you this, that if I were doing this, I wouldn't be bantering too much about the whole thing. I'd just use the likelihood function. I like using likelihood functions. I'd probably use a beta half-half prior and do base them. I'd have all kinds of good reasons for doing that. Saying that, there's other ways to do inference. So let's imagine if you were not a Bayesian or a likelihoodist at all, and you like to violate the likelihood principle. So one such concoction is evaluating p-values. So this might trip you up a little bit, and I'll walk you through these p-value arguments. I'm going to just write down in general. This is y. This is going to be the number of failures. This is how I'll parameterize it. Plus the number of successes minus 1, choose y, times p to the number of successes, 1 minus p to the number of failures. So that's what that function looks like in general. And I'm going to let the number of failures be random. So if you plug in the number of successes and the number of failures into this, you get that. This is just the probability of seeing all those failures.
In the choose, would be choose y minus 1.
Oh, you could. So it's going to be choose y, right? Oh, this is where we're. Yeah. 9 o'clock. So yes, that's right. Good. So still same likelihood functions. Okay. So let's do something that violates the likelihood principle. P-values don't have anything to do with likelihood functions. Agreed? What's a p-value? We haven't even touched it in this class, except for the definition. We will get to it in chapter 8. But everybody knows what this thing is. And if you haven't heard, some people argue over the usage of these things. So, and I'll be presenting you with quite a few papers about debates over the utility of p-values. Not all p-values are the same. Some of them I look at and I don't wince. I go, okay, I interpret it a little bit differently than you, but that's a satisfying argument. And some p-values I look at and I think I would never touch that thing. So we'll get into the difference of different types of p-values. So it's the sharp null one that's usually contentious. Okay, what's a p-value, just in words? Nobody wants to say it because it's too easy, or because, geez, Stat 101, they always ask me to say it, and I say it a little bit wrong, and they kept like slapping me for it. What is a p-value?
It's the probability of observing the data you did under some null hypothesis.
Everybody buy that? The probability of observing your data given the null hypothesis. Or more extreme, and that's an extremely important thing. So you're going to be summing over the sampling distribution. So you're not using the likelihood function, and you're plugging in the null hypothesis. So that is not a likelihood evaluation. So the p-value is the probability of your data, your observed data, and more extreme data, less shade. Given the null. We're going to untangle all this, understand all the mathematical repercussions of this when we get into hypothesis testing. So, but let's just do a hypothesis test for both experimenters and see what goes awry. So let's just write down the null hypothesis. So for our example, I'm just going to arbitrarily pick this. H naught is going to be P is equal to P naught. And H alternative, you always set up an alternative so you know which tail direction to sum over. I'll pick one arbitrarily. This is not the sharp null test right here. This is the one-sided test. This is not a contentious test all on its own. What's going to be a contentious here is that this integrating constant that they have, the normalizing constant, is going to really make a big difference in this calculation. So this isn't the traditional super contentious thing that I'll harp on. I'll just show you what goes wrong if you don't adhere to the likelihood principle. So just some arbitrary hypothesis. Let me just ask a question. What is the probability that P is equal to P naught? I think so too. So I always think so. So when I hear this question, I usually think, what do you really mean? What are you trying to ask? I think what you're trying to ask is it close enough to P naught that you would be willing to accept that as an answer? So we'll come back around to that, but I think that's the question we want to ask. I think I already know if I'm talking about a continuous parameter, what's the probability that I'm actually going to guess the right thing? And anybody that's studied numbers, the real number line, knows that that's a vacuously small thing that can happen. So vacuous that we call it probability zero. Doesn't mean you're wrong. Doesn't mean it won't happen. It's just so small compared to everything else. So I don't believe you if you actually say, no, it is. It's absolutely that. So we'll get into that statement later. The reality is all this contentious stuff, what we're arguing about is relative distances versus absolute distances. And that's it. Okay, so experimental one. Computes p-value. We're going to do it like this. X is going to go from 5. This is going to be my observed data. Up to n, which is 10, right here. So n, choose x, p naught, x, 1 minus p naught, n minus x. So what Jacob said is we have to condition on the null hypothesis, so we condition on it. We're actually conditioning on a limit of the one-sided test. We'll talk about that later. So what we're actually doing, what the name in Pearsonian is saying when you actually plug this in, right here. But that's how you compute this thing. And if you've taken a Stat 101 class, this shouldn't be too elusive. So this is more extreme data, probability of seeing your head and more extreme stuff. I'll point out that in this hypothesis, what I always do is see if I've summed over the right direction. This is the brain teaser. The right direction to sum over. If you make P naught bigger in this equation, this thing gets bigger. You can probably see that, but if you can't, take it to your computer and evaluate it. So bigger P naught makes this thing bigger. If this sum is small, it means that P is probably bigger than P naught. So that's the logic of this p-value thing. This sort of contradictory evidence argument. It's a brain teaser. So I'm going to use unlikely stuff that didn't happen in the first place to evaluate something that I don't think happens in the first place. That's how I usually interpret a p-value, just to make it seem extra confusing, but that is what it is. So we're using stuff that probably didn't happen and didn't happen, so in this equation. So we're summing over a tail probability. So this is the probability of 5 or more heads. Don't worry, I'm not going to ask you to compute these sort of Stat 101 p-values on my midterm. I'll assume you know how to do that. So I don't want to reinforce this too much. But this is the p-value. So if p naught is small, or this p-value is small, then maybe we reject in favor of that, the p had to be bigger than p naught. Maybe you buy that. But that is the correct p-value that you would come up with for this hypothesis. Let's look at experimenter 2. Experimenter 2 computes I'll write it up here. They're going to sum over something as well, but we're looking at the tails now. So flip everything in your mind. So experimenter 1 is summing over the heads. Probability of 5 or more heads. Experimenter 2's random variable, might be too early for this, is tails. So you flip the summing direction. So we're talking about the other thing. This is going to be y plus 4. So this is my successes minus 1. Choose y minus 1. P naught. This is going to be my successes, number of successes. How many successes did we see? We saw 5. This is going to be raised to the y, the number of failures. This is the part that might have you slightly confused. But I'm going to sum over this thing. Y goes from 0 to 5. So I'm summing over the left tail because I'm summing up the tail, the failures. I'll let you play around with these and convince yourself that these are the correct p-values for testing that null hypothesis. Okay?
Question, is it really choose y as was originally done because you have y number of tails to choose to fit?
What's that? Yeah. So you want me to write this, choose y. So yeah, I agree. So we're going to sum over that thing right there. And so here's the kicker in the argument. This thing, and this thing, and I'll let you plug in numbers if you'd like when you go home. They aren't the same numbers. So star, star, and star are not the same. Here's the punchline. Star is not equal to star. I'm sure that there's some value of P naught in all these arguments that you can make them equal, but in general, they're not equal. So if you just pick some numbers, evaluate those sums, they're not gonna be the same. So the punchline is that they're not the same. So if I use this p-value thing, I'm summing over the mass function and not using the likelihood function, I can come up with different inferences because I disagree about something that seems so mundane, like the stopping rule. The stopping rule changes the integrating factor, the normalizing constant. And that is needed when you evaluate a p-value. And so I think that's pretty compelling, that I have to understand exactly the process. Now, Fisher would probably come back and say, yeah, that's right, you need to understand exactly the process. And he was into designing experiments, and he knew what his stopping rules were. And so that wouldn't happen to him. So this is a little bit fictitious, but we do see data all the time in the observed world. I work on mostly observational data, not well-designed experiments, and I forecast from it. And I don't know how it was generated. I don't know if there was a real generating function, you know? And so I don't want to run into this trouble of summing over more extrema. There's also other problems with p-values. Sometimes it's not well defined what more extrema means. Difficult to understand. So if you're in a bimodal situation, what does more extreme mean? No clue. So we'll get into that. But this sets people up for an argument. So you'll hear people come in and say p-values violate the likelihood principle. And the p-valuist will come back and say, yeah, but I don't have to adhere to the likelihood principle. And the likelihood principalist will come back and say, well, do you adhere to the sufficiency principle? They say, of course I do. Sufficient statistics have all the information about the data. Do you adhere to the conditionality principle? And that's where you might argue, right there. But I think it's an okay thing to do to condition on your data. So I kind of like just looking at likelihoods and going, that the answer's somewhere around here or here. And that's kind of how I think about it. So it doesn't seem all that contentious, but it's certainly an argument that you're setting up that if you use a p-value, you can be in trouble for arbitrary reasons. Any questions about that? So I'm going to ask you this throughout the class. I'm going to ask you, as we go into estimation methods, did we just violate the likelihood principle? And then I'm going to ask you if you care. Then I'll tell you what I think. And I think that that's good enough for us. So I don't think it's worth going back to the proofs and trying to argue that you have to do this. But I think that this is a good guiding light. So this is one of my principles that I use. And when I violate it, I often ask myself, was that okay? Was that an okay thing to do? Keep in mind, it's all a little bit of a fiction because we don't always have model in hand for modeling in the first place. And modeling in the first place is a violation of the likelihood principle. So for instance, let's say I write down a model. I go, that data looks like this. I'm going to presuppose this model. And then I fit the data to that model. And then I evaluate diagnostically how good the model is by looking at residuals. And then if I see that the residuals are doing something funny, then I change everything. Violation of the likelihood principle. And I do it all the time. So I think it's okay to violate the likelihood principle. I used to get really concerned about this, and I'd go to Jim and I'd say, what do you think about this violation of the likelihood principle? Because you do it. And he says, oh, it's a minimal violation. It's not a big deal. And so I don't know. So he's the governor on minimal or maximal violations. I'm not quite sure. So, but maybe residual checking is like jaywalking, so no big deal. But everybody does it. Just keep in mind there's no such thing as likelihoods over likelihoods. And so you can construct that concept, distributions over distributions, but we don't really know where these likelihoods come from in the first place. We come up with them. And so philosophically, it's an interesting argument. I'd be willing to have it with somebody just for the logical debating back and forth. Let's spar with each other over semantics, logic, and what this statement is really about. Saying that, I kind of like just the example of seeing what can go wrong. And I have a book on this, and I was thinking about bringing it in, but my book's like $350. So if you ever want to see it, you can come by my office and I'll show it to you. But it's Jim and Robert Wolpert's book on the likelihood principle. It looks like a typewriter made it, and the reason it's expensive is because everybody threw their books away a long time ago, and they're not around anymore. And so it's just an artifact nowadays, and I really like it. I think it's cool, but it's hard to get that look. What you can find is just examples as to what can happen if you violate the liquid principle. I think I'm going to leave it there. And we'll pick up next time with estimation, which I think is really what this class should be about. So for the future, I am going to tell you all about hypothesis testing because there's a lot of nitty-gritty in there that we have to be aware of. But what I really care about in this class is whether or not you can estimate well. And so I'll let you decide and fight over how you want to do your testing, but I'll tell you all about the repercussions. So we're going to spend a lot of time on estimation, chapter 7. This is probably the funnest chapter because it's just a lot of calculus. So you know how to compute things, you can come up with answers, and we'll compare the answers under different paradigms. And then I'm going to show you how to do the computation as well. So we're going to also be studying the EM algorithm in the next couple weeks. So if you want to have a quick glimpse at that, that would be helpful for the future. That's it, you guys. Have a great spring break. If you didn't grab your homeworks, I got some homework ones up here for you.